Welcome. This is Dr. Hisham Said, and this video here is the second part of our discussion related to transformed stresses. And in the first video, we learned about how we relate stresses at any angle of a section relative to another section with a difference in angle between them as theta. And this is basically the formulas we learned last time. So sigma x prime, sigma y prime, and tau x prime, y prime. And they are a function of the given stresses at the original orientation of axes, so sigma x, sigma y, and tau xy. And considering the angle between the original axis orientation and the orientation of the axes for the transformed stresses. So we will learn here the amazing circular relationship that exists between these transformed stresses and their orientations also. So we're given here this stress block 2D, and it's here we're given the sigma x, sigma y, and tau xy. And the idea is we would like to plot, using Excel, to plot the values of sigma x prime, tau x prime for theta ranges between 0 and 180 degrees. So kind of figuring out what's really the type of relationship that exists here between sigma x prime and tau x prime with theta. And you see here, I'm acknowledging that this is a tension, so it's positive stress, compression, negative stress, and that type of tau here, the direction of it is positive as we discussed before. So when we use Excel, like plotting different theta, and for the values that are given to us, sigma x, sigma y, and tau xy, we end up with these values for sigma x prime and tau xy prime. Plotting them will show us a perfect circle, and that circle here is the one that we will use to simplify our way of analyzing stresses, and actually it will give us more deeper understanding of stress transformation beyond just the formulas that we have seen before. So it's based on the formulas, but that graphical circular relationship will show us the relation between stresses, the transformed stresses at different orientations. So one thing, let's sit straight here, that when we draw the shear stresses on the block, that's a positive shear stress. And we're thinking now to plot it on this circle and finding kind of this point of that stress here to represent it on the circular kind of graphical representation of transform stresses. Plotting it positive is incorrect. So it's a positive on the stress block, but it should be plotted negative on the circle here. And the point here is if on any surface, when I plot here the stress, if it's causing clockwise rotation around the center of the block, this means it should be plotted as a positive value. It should be above the axis. But if it is causing counterclockwise rotation of the block around its centroid, then that's kind of will be plotted as negative or below. So as a kind of a nice kind of a little song here, in the kitchen the clock is above and the counter is below. So kind of will help you when you plot tau values in that circular, and we refer to that point, and it will help us when we figure out the change in orientation to figure out maximum stresses at a point. It will give us the correct orientation if we plot tau in this way. So it's a little funny kind of tweak, but it will result in the correct orientation later. So stick to it, and that will help you to get the correct answer at the end. So now if I plot, I have a stress block. It has two main faces here, sigma x tau xy and sigma y tau xy. So what happen is I will plot these 2 points because they represent the other two faces and the whole stress block. So if I plot them, and remember now sigma x in the face of the block, so on this one, as where sigma x is, this is a positive direction. So it will be going, my positive in the block is a counterclockwise rotation of the block around its rotation or centroid, which means it will be plotted negative. So this is why I always kind of related to that change in the sign I'm plotting tau in this circle, is that when you plot sigma x, flip the sign of tau xy that's given with it, and then sigma y will be the same sign that's given on the stress block of tau. And now when you plot these 2 points, they represent one stress block and represent one state of the stresses at this point. So they are forming here a nice diameter, one possible diameter orientation of the circle. So between these 2 points here. And that circle, I can also, as a circle, I can know the center of it, which is here, it's the sigma average, or the average between this x coordinate of this point and this point, which is basically sigma x plus sigma y over 2. So that's a circle. I need the center, and also I need the radius of the circle to be able to define completely the circle on any point on it. So the radius here is defined by I can figure out the value through this triangle, and r here is basically the square root of the top or the vertical side of this triangle, which is tau xy, so tau xy square, plus the horizontal dimension of that triangle, which is half of the distance between sigma x and sigma y, so half sigma x minus sigma y over 2. So this is why I end up with this radius formula. So as a circle, I define it as the location of its center, so sigma average, and the radius of that circle. Now we'll get some now interesting findings using the circle. So I can know where is my, what we call principal stresses. Over here, the largest possible normal stresses at this point. So at some rotation, at some orientation, these maximum stress happens. So I have here maximum stress, maximum principal stress here. Well, the largest one, I will call it sigma 1, so it's equal to sigma max, which is to the right of the circle here. It intersects with the sigma axis. And then the sigma min is equal to sigma 2. And from the circle geometry, the sigma 1 is equal to what? It's equal to sigma average, that coordinate here, plus the radius, because that's the radius here. When it goes like that, rotates, so it's actually this distance here is the radius. So it's sigma average plus sigma plus the radius. This is sigma 1, and then sigma 2 is equal to sigma average minus the radius. It will give you sigma 2. And this state of stresses, where I have maximum stresses, principal stresses, this happens at angle what we call theta p. That's another finding here, that the angle that I measured in the circle is actually double the angle that happens in reality. So these angles here, remember I plotted 0 to 180 when I developed this circle. So 0 to 180 gives you a whole circle. So every one of any one angle I measure here is actually representing double the angle in life. So in this case, if this is my original state of stresses and I'm transforming them to be the maximum stresses, so I'm rotating here counterclockwise, this angle here I will call it 2 theta p, but in real life it happens at theta p. So half of it only is the one that's really happening in real life. So when I rotate now, that 2 theta p, using that same triangle that I figure out the radius, this 2 theta p is equal to tan inverse of this upper side or vertical side of the triangle, tau xy, divided by the horizontal side of the triangle, which is half of sigma x minus sigma y. And that will give us this sigma theta P, theta of principal stresses, as shown here. And you can see here, that's my original state of stresses that represents that solid black line or diameter of a circle. Now following the direction of rotation here to move from this diameter to that diameter, the flat one, this means that this stress block, to the orientation where I will have the maximum normal stresses will be clockwise, counterclockwise of theta p. And you see here, remember, every point represents a combination of normal stress and shear stress on a face of the block. So if this is sigma 1, I have here 0 ordinates, so this means that tau is equal to 0. The same thing for sigma 2. So the new stress block that represent principal stresses have 0 shear stress. So sigma max or sigma 1 here was 0, so I'm not drawing any arrows for the shear stress here. Another thing also that I can figure out, so I figure out the principal, which are maximum normal stresses. I can figure out where is the orientation of the maximum shear stress. So the shear is my ordinate, right? So the vertical, dimension here, the highest point and the lowest point of the circle will give you the location of your maximum shear stress, or the orientation of the maximum shear stress. So that blue, heavy line here, that's where tau max will happen. And remember, when every one of these diameter is a possible state of stresses at a point at different orientation, so they represent the same tau stress happening at different faces. So this value here is positive value similar to this negative value of tau max, and they happen at exactly at the center of the circle, top of it and bottom of it, or below it. So this means that I will have a stress block that will have tau max on all faces, and the stress will be normal stress on the faces of the block will be equal to sigma average. So it will look something like that. So tau max, if my sigma here, this is sigma 1, sigma 2, and it's positive, and this one is positive also because the whole circle here is on the right side of the tau. So sigma max, sigma min are positive, but this is bigger than that one. Sigma max is bigger than sigma min. If I rotate here 90 degrees in the circle, which is interesting, I can relate the principal stresses with the maximum shear stress. If I rotate 90 degrees in the circle, that refers to 45 degrees in real life. And that 45 degrees now I have here sigma average on all faces, applying positive sigma equal to sigma average. So that's a sigma prime here. And now my shear stress is equal to tau max. So this one, sigma max, will change from this point, which is the principal maximum stress, to this point, which is a less value. And this point here, this is a positive tau. So now I'll plot it, a positive tau, remember above is what? Clockwise, right? So I'll draw it as a clockwise tau on that face. But this face here, or that point here, is the rotation of point B to point A. So, which is point B is this sigma min, is rotating to be that face, so it's also subject to sigma average. But now tau is negative, so below is counter. So I draw it as counterclockwise, the shear here. So be careful about moving, especially the confusing part here is a little the matching the orientation of tau on the stress block with the values of tau on the circle here. And that circle, we'll call it Mohr circle. So Mohr circle, M-O-H-R, it's the circle that relates the stresses, transformer stresses at all possible orientations that I have at a point. One interesting observation here is that relationship between the orientation of maximum normal stresses, principal stresses, and the orientation of maximum shear stresses, that actually can help us understand more the behavior of materials. So in tensile tests, when we applied tension on at the ends of two rodi or specimen, from the lab tests and experiments he did, in the lab, you found that ductile material usually have that cone shape. And the key here thing that ductile material start the failure by at shear. So they exceed their shear capacity, and the shear failure here happens at the surface of the cone, which is actually 45 degrees. So in that state, loading case, I have only pure axial loads if I cut perpendicular to the axial load. So I have pure normal stresses, which is this case. But at 45 degrees, I will have the maximum shear stress, and this is why if a ductile material fails under shear, this will happen at 45 degrees. But brittle materials happen or fail under normal stresses, and if this is the load case here, the maximum normal stresses are at exactly a cut perpendicular to the normal stress here, or the axial load that I have. So that's why their failure is exactly perpendicular to the axial load that I applied at this specimen. So let's see here this, back to this circle here, and try to understand it more by looking at it as really a circle and trying to see where are the principal stresses happening and maximum shear stress. So I have here, this is the circle, and I kind of summarize the block of stresses here as values for sigma x, sigma y, and tau xy. And you can see here, if I plot here sigma x and negative tau xy and sigma y and tau xy, that will give me one diameter here of the circle, and this diameter represents exactly that stress block that's given to us. It's just a representation of it. So every stress block at an orientation is a diameter at an angle of this circle. Now the center of the circle is with this diameter intersects with the sigma axis, and here it's the average of sigma x and sigma y. And I can see that now the circle intersects with the sigma axis at the principal stresses, and that happens here due to the rotation of my stress state block by 2 theta p degrees, and it's counterclockwise. And my stress block in this case will be sigma max here is actually tension, and sigma min is on the negative side of the axis, so it's a negative, it's a compression. And of course, they intersect with the sigma axis, so tau here is equal to 0. And another thing also I can see from the circle is the position or the orientation of the maximum shear stress, which happens with sigma is equal to sigma average. So sigma average for both points, but then tau max here is given to us as the utmost, highest, and lowest points of that circle. And if I draw the stress block here, I will end up with sigma average normal stress in all faces, and they're all here positive. They are to the right side of the chart. And tau max here, if I check it, sigma average, that's coming from the rotation of sigma x. If you look at the point of sigma x and negative tau xy. In the stress block, the sigma x was positive and tau xy was positive in the stress block. So, and here the rotation of the line from the original state of stresses to the maximum shear stress, that didn't change where I moved my tau. So tau here in the chart is negative, right? So tau here is negative on the chart when it's plotted with sigma x. So in the stress block, it's drawn here as positive, right? So that's the key here, that I'm trying to be careful about switching from the circle, Mohr circle, to the drawing the stress block that represents the real life behavior of that point and its stresses. So that's the very cool graphical representation of transformed stresses. It will help us a lot in understanding more deeply the transformation of stresses. Mohr circle is a very, very important tool, and it's very fundamental when you move to advanced classes in strength of material, machine design, structural analysis, to understand the development of stresses at a point. The orientation you use or you choose to analyze or calculate internal forces and internal stresses at the point doesn't mean that this is the orientation that the failure will happen. You have to figure out the orientation of principal stresses and the orientation of maximum shear stresses. All right, that's it. Next part of this lesson will be like giving, solving an example just to illustrate more circle, and we'll see more on using Mohr circle in solving transform stresses. All right, thanks for watching. Hisham is out, and peace.